Swayam Prabha. Digital India. Educated India.
Welcome everyone to the afternoon and the lab session. So what we're going to do now is take a closer look at the Docker and Kubernetes environment. And before that, just want to summarize what we learned in the second half of the session earlier. So we talked about the networking challenges, a container running inside a program running inside a container will have a port that is unique to the isolated space in which it's running, and the external world does not see the container, only the host. So there must be a mapping between the port number that's seen on the container and the actual port number on the host, and the network settings that are specified when the program is containerized tell the container runtime to bridge the ports, and that is done when the image is downloaded and instantiated as a container. And when the one container wants to talk to another container over the network, it cannot assume that it is always available on the same node or even in the same network. So it will have to depend on some kind of a DNS service to find out where the service exists and act accordingly. This is in tune with how you would see any other network related communication. And in the second part, what we saw was the persistent storage. There is an ephemeral storage. So if a container starts up and tries to write to its local root directory, it never really goes to the actual root directory that was instantiated out of the image. It will go to a temporary directory, and that probably will get discarded when the container is deleted. And one way to preserve whatever data is written to the local storage across container restarts is to make that storage as persistent storage. And the way to make persistent storage, the inner mechanics is that the directory which has to be made, which has to be presented to the container must be first imported into the host via any mechanism, and then it is bind mounted into the container namespace. And we saw that when we looked at the mounts section, when we inspected a particular Docker image. And later on, we saw that what about external storage? Like if I want to import some storage from an external source, such as a EBS block device from Amazon, Elastic Block Service, or if I want to import Azure Disk, Microsoft Azure Disk from Azure Cloud. What if I want to import a GCP Google Cloud Disk into my container? It's a two-step process. First is, again, as we saw, the disk must first be imported into the host, and then the host will bind mount it into the container namespace. So these things, especially when the ones where you have to deal with an external storage, are handled by a component called a CSI driver. It is called Container Storage Interface Specification. And for every kind of provider, there is a corresponding CSI driver. For example, Amazon's Elastic Block Service has its own CSI driver. Google Cloud Platform has its own GCP driver, and so does Azure Disk. Azure Disk, there is a corresponding driver, and if it was HPE's storage platform like HPE 3PAR, HPE has its own CSI driver. So how that works is whenever the container is to be scheduled on a particular node, Kubernetes master node tells the agent on the node, which is the kubelet, that come on, start this program. And when it looks at the program, it says, okay, it needs storage of the type HPE storage. So I'm going to start the HPE CSI driver, the specification of which will be available in the Kubernetes spec itself. It will pick that up, and it will first probably deploy the CSI driver, which will bring the storage to the local host. And then it deploys the container and asks the CSI storage to bind mount it into the container namespace. So this is a sequence of steps which is quite intuitive, but the mechanisms of it is not quite obvious if you simply read the general documentation. So this is an important concept about how simple everything is made, yet it's very elegant and extensible. So what we're going to do now in this lab is we're going to go back to our Ubuntu system, and we'll do two parts. One is what if we want to launch a container from an ops perspective. That means if I want to start a container from Docker, a container runtime, how will I do it? So to do that, we will enter into the virtual machine which is running the Docker, go hands-on on it. We will use some command line options and we will deploy it there. And next we will see how the same thing can be done in Kubernetes. It is done slightly differently using different type of specifications, but the underlying mechanisms of what happens is the same. That means it will not change based on whether we are using Kubernetes or whether you are using Docker. So with that, let me start with the Docker host. So I hope you have your Ubuntu systems ready. So you can actually start the Ubuntu system. I'm trying to find the chat window here. So I'm going to, I don't see the chat window here. So let me open up my, okay. So I have the chat window here. So what I'm going to do is I'm going to paste some commands that I'm running here. So if you have a Docker environment, for example, setup, you will see that these commands are pasted uh, onto the chat window, and you can simply cut and paste from that into your Ubuntu system. Does anyone have any questions or comments before we get started? Okay, great. I'm unable to find the chat button in my, okay, so maybe it's in the main window. Just give me a minute while I figure this out. It's taking a bit of time. So I think the so I'm unable to find the chat window here. So perhaps what I can do is it's taking forever. So I'm still unable to find the chat window for this meeting. So what I'm going to do is maybe instead of trying to spend any more time here, we will get started and I will show you the text files on the screen that we are going to use to deploy the containers, and you will be able to do that. So let's get started. So this is the, later on I will share all these files with you. But for now, if you are also in the process of deploying these containers, please note down this. These are not very complicated ones to copy. So I wish that I could post it on the chat window. I have these files, but for some reason I am unable to locate the chat window here. Or it's usually for every meeting it should show up on the chat window. Can anyone post something on the chat window like a hello or something and see if it pops up on my screen? Anyone? Okay. You guys are able to hear me, right? Are you guys able to hear me?
Yes, sir.
Can you post something in the chat window? Do you see a chat window?
Yeah, sir, we did.
Oh, I am unable to see that. So I'm wondering what's why I am not unable to see the chat window. It's kind of hmm. I think since I'm unable to see or access the chat window at all, this will not be helpful to show the comments, but let me show that on the text. So what we're going to do is first we are going to run a program called Redis. So I think you have heard of uh, this key value data store called Redis. It is one of the open source tools. It allows you to store an arbitrary number of key value pairs. So we are going to do it in the Docker first. So we're going to deploy Redis from Docker. So in the first step, what we're going to do is we will deploy the Redis and we'll look at what metadata has been created to run Redis. And we're going to stop that container using the docker kill command, and we're going to remove the container. And next we're going to start the same container again, but this time we will bridge the ports. That means we will bridge the port from the Redis running inside the container to the port number on the host by using the -p option. And once we're done that, we're going to kill that again. Next time, we're going to start with the persistent storage given to the Redis container. And we will again inspect what happens inside the container. Fair enough? So let's do this. And I wish I could paste all this into the chat window, and for some reason I'm unable to do that. So I will share that this with you. But in the meanwhile, let's copy into this. So first I will run this command. Let's see what happens. Copy this. Now I'm inside the virtual machine. So what you're seeing now here is it did not find the Redis image. Just you will see that it's steadily pulling the image. This is the stage where it is being pulled from the repo. So actually it is pulling from the public Docker Hub repo. It's about 28, 30 MB, and you will see that steadily progressing. And fantastic. So what you see here is once all the layers that consist of Redis image has been downloaded, it generated a unique ID for it, and it said, okay, I downloaded the image that you wanted, and it instantiated a container and it printed out the container name. Now let us take a look at how it looks once it's run. I'm going to copy this command and paste it here. Let's see. So you can see that Redis latest has been deployed 36 seconds ago, and it is listening on port 6379. And the name that has been given to this is MyRedis, because observe it here. I have given the name that I want to refer the container as MyRedis. Fine, it's running, and let's take a look at what's inside my Redis. Let's look at the network settings. You can see that it has requested networking services, but you will also see that there is no port mapping, even though the Redis server is listening on 6379. That is the left one of the colon here. It says the container program is active on port 6379. Externally, it's null, meaning it is not visible to the outside world. So if you try to connect to it, you will probably get nothing, and you will see that the environment variables have been set and the image has been specified. And here you can see volumes. That means the Redis program is expecting some data to be written in. It tries to write some data into /data directory, but externally it's not been given any storage. So it remains empty. So whatever it writes into /data will be lost when this container stops. So similarly, you will see that plenty of other things such as the graph driver, where exactly the image was downloaded. You have the merge directory, upper directory, and the working directory, and the file system is overlaid to when it's instantiated. Here you will see that many of the proc keys are running here, which means not everything is visible. So it has these are all the various restrictions that have been placed on Redis. Quite an interesting read actually. If you do a Docker inspect, it will tell you all the restrictions that have been placed on this container, what it can see, what it cannot see. Now let's do a little bit of inspection. We have looked at what the container is by inspecting it. So we did a Docker PS and it showed that the container was running. Now let's stop this container. To do that, we'll use the docker kill command. And it said it killed. Now let's see, has it actually killed the container? Copy and window paste. Yes, container is done. But even if the container has been killed, the container that it generated, that means it deconstructed the image and created a container out of it, that still remains on the system. So which you can verify by doing this. You can see that it has exited and it was running 37 seconds ago. And this is the image that we had downloaded. So what we can do is and it's removed the container image also. So here you go. We have gotten rid of the image. Now let's redo the same thing by connecting the ports. This is the important thing that we're going to do this time. That is, we are going to run the same thing, same command that we ran before, except that we are adding this portion. That means we are requesting it to map the port and connect it to the external port. So let's see what happens. Very interesting thing that you might have observed here. First thing is, the first time when we launched it, it downloaded the image from the repo and it was doing, you saw many messages like downloading and pulling the layer and everything. That is not done this time. And the answer is obvious because the image is pulled only once. And the next time you want to instantiate a container, it sees that you ask for Redis latest. It was already downloaded previously. So it will use the same image to instantiate this container, and the new container has this ID. Now let's look at the containers that are currently running. Great. You are seeing there's a slight difference in what you're seeing here. That means same image and it was launched 44 seconds ago. Can you see this one? Here it says, even though the Redis is listening on 6379, on the external host also, it has been allocated 6379, and the name of the container is my Redis. And this we can further verify or take a look at. Sorry. Let's do it. Everything looks the same, and you can see that it has, when it was started, it was asking for 6379 as the TCP port, and it has been given TCP IP port. Everything looks good. And it's the same what we saw before. Now, here is the important part that you see, that is 6379 on TCP has been given on the external port also. This is a difference that you will notice from what you saw earlier. So when we specified, this is how we open up a networking port, and the container runtime has done the necessary things to connect these two ports. So any program will be able to reach my Redis from an external network. It is no longer isolated. The experience for the external program will be exactly the same as if it was accessing Redis on the host without being in a container. Again, let us stop this container. We'll remove this container. Now let's do the third part of it, which is we are going to run the container, and we're going to open up the port here saying the local port will be 6379. I want it to be connected to 6379. And by the way, I would like the local directory, that is the Redis. I have, if you look at the current directory I'm in, I have a directory here called Redis. Sorry, let me make. Okay, so let's keep a file here, touch. And I want this directory to go to /data inside the container. And I'm going to say this is what I want. And let's see what Docker does with this. It does exactly as it's told, which is okay. I think there was a Redis directory here. So here, let me do that. It actually comes from right. We have placed it, and let's look at the container that. Fair enough. We have started the Redis container again, and as you notice, it did not download the image. It has mapped 6379 to 6379. Now let's look at great. So here we saw same as before. 6379 has been mapped to 6379. Fantastic. Okay. Observe this section. Because of the command that we executed, which said, I want the persistent storage coming from the host, from home Docker Redis, and I want it to be bind mounted to /data inside the container. And I want it to be read write, and I don't want it to be exposed to any other containers. And rest of everything else remains the same, all the proc and everything. So great, let's look at what it has done here. So let's do one simple experiment now. Let's go inside this Redis container itself and see what happens inside the container. But before that, we'll get there also, because we want to see from the container's viewpoint, what does it see? So this is the Docker host. Look at the root directory. This is what the root directory looks like on the Docker hosts. Let's look at all the processes that are running. Oh, there are so many processes running. Very standard for all the any Ubuntu system that's running. It's running all these processes, and we'll look at one of the things that we will do is we will use a command called docker exit. We'll enter the container and we will see what's happening there. So here we are inside the /data directory of the container. But before we let's look at what's created there. Wow, we'll see the file that we created on the Docker host is present here. Now let's see what our processes look like. Okay, there's no ps command. Let's go to proc file system. And here you will see that on this particular in this particular container, it has limited visibility. That means it has no visibility to any processes other than 1, 20, and 29. It has very little visibility on what devices it sees. There are hardly any devices. And let's look at its root directory. You will see that it's very different from what you will see on the host. Now we are in this directory. Let's do some let's say fantastic. We have written this data from within the container. And now let's exit the container. We're back to the Docker host. And just to prove the point, here we had gone inside the container's proc directory, and we saw there were only two processes, 1, 20, and 29. What's the story on the root file system here? Can you see there are so many processes on the real system, on the host system, but the container was able to see only what it was allowed to see. So if it did a PS of trying to look at what other processes are running, its visibility will be limited to just 3 processes and nothing else. Whereas on the actual system, there were all these processes that were running. Right? So well, let's look at you will see that there's a Docker service. This is our C group inside it. Docker service has tasks. It is controlling this many tasks. It is going to connect container. So these are the tasks that are under control for this CPU. I mean, this is the contain. This is the C group modifications that has been done when we launched the MyRedis container. Great. Now let's look at our Redis directory, where this is what is bind mounted into the container's volume, and bingo. So from within the container, it is able to write to the file there. And because it is bind mounted, it is also visible. So when we remount the container, the same file will be present. It will continue to persist beyond the lifetime of a container. Let's Docker kill my release. And you will see that we had downloaded Redis. It's still there. Let that still be there. We are going to use that for Kubernetes. So this is how these are the three scenarios that I wanted to show you. That is this is how you deploy it by hand, and you were able to see its usefulness about how we can inspect the container and we can do all this. But the same thing can be done from outside of this Docker host. So what we are looking at in this terminal is this is inside this terminal is we have done minikube SSH. So we are inside the container host, and this is the host that runs all the containers. As you can see, Docker PS running all these containers. But this is the host. From here we can do kubectl and cluster info. Get pods. Now let's try and deploy the same MyRedis. If I have to deploy the same application from Kubernetes, how would I do that? So let me show you the. So the most important thing in Kubernetes first is you create a deployment file. That means you tell what you want to do, and then you contact the API server, and it will do the rest. So let me walk you through a particular file about how we are going to create a deployment. First, we are going to create a YAML file that says I want to deploy, and I want to call this Redis deployment. And these are these very standard ones. You do not have to memorize or by heart any of this. You can simply download a sample YAML file and modify this. So what I am telling here is this is my Redis is what I would like to call my application. The name of the deployment is Redis deployment, and it has one app called MyRedis, and I would like to have two replicas of it running. So you may remember that when I did it from the Docker, I simply deployed one container of Redis, but here I am telling Kubernetes, I want two. Remember, this is declarative. I'm not instructing Kubernetes how to start two replicas or where it should run. I'm not specifying which node to run. I'm not specifying how to do it. I'm simply saying I want two replicas. I want it to be run, and the application called MyRedis will be based on one container, and it has to deploy redis.latest. And I want to open up this particular port. So this is called declarative. That means I don't instruct Kubernetes how to do it, and Kubernetes doesn't know how to do it. It will actually delegate it to the kubelet program that exists that runs on the container host to figure out how to meet this requirement. So let's see what are all the steps that one does to deploy this. So let's next. These are the set of okay. Okay, great. So the first thing that we are going to do is we just looked at the YAML file that specifies a new type of a deployment consisting of an app that I would like to call MyRedis. And I said that app contains one container, and that container has one port that needs to be opened up, and I want two replicas of that. I specified that declarative specification. So let's kickstart the process and see what happens. And remember that I am doing this from outside of the container host. I am not, this is inside. So if you look at Docker PS and Redis is not running anywhere. And I have killed all the containers that were running Redis. But now I am outside of that host, and from sitting somewhere from outside of the Kubernetes cluster, I'm controlling how it should be deployed. So I will say mine is there. Right. Okay. Deployment created. So let's see what it did with it. So it said it's up to date, it's available. 9 seconds ago it started. So this is the status from the Kubernetes viewpoint, that you wanted the 2 replicas of it, out of which 2 you wanted 2, and out of which 2 have been running, and they are all up to date, and it's been running for 9 seconds now. Let's go inside and our Docker host and see what exactly happened there between these 2. Okay. You can see that it has started 2 copies of this. That means it's called Redis 3. It has given it its own name. When I had started it by hand inside the Docker host, I had given it the name myredis. But here you are seeing, before we ran the kubectl -deploy command, there were no Redis images running. Now 2 containers are running. Why are there 2 containers? Because we asked for 2 replicas and it followed our command. And here there are, it has probably started 2 more. To essentially, it started them in a pause state and it will likely restart it if one of them were to go down. So this is some of the optimizations. Because I did not tell Kubernetes how to achieve the replica set and how to keep it, how to keep 2 things running, it has taken a decision on its own and it will meet my requirement by any means necessary, but whatever means are possible. So let's go back to our Kubernetes console and let's remember we did Docker inspect and we looked at the containers. Similarly, on the Kubernetes side, we are going to ask it to describe the deployments. Here, it described the deployment in a much better formatted for human reading. It says this is the deployment you wanted, and I created it. This is when I created it, and I have you ask for 2 replicas. You ask for 2 desired replicas. 2 have been updated. Total 2 are available. And strategy type is rolling update. Very interesting one. So it says if I ever ask it to replace it to a later version of an image, because let us say some Redis developer pushed a new image of Redis onto the repository and I want to update it, and I can simply ask Kubernetes to refresh it to the latest version. So the way it will do it is it will not stop both the containers. It will stop one container first and then restart with the new image. Then it will start the second container and then restart it with a new image. So this is called a rolling upgrade, which means the deployment, that means the program will never actually be completely unavailable. One copy of it will continue to run. This is a rolling update. And you can see that I really did not have to do any of the management or any of this instruction set of how to do this. Kubernetes figures out all this on its own because it is declarative. And here you can say that, here you can see this is the port that has been opened up 6397, and on the host side, the port number has been given as 0. Actually, I should have given it as 6397 on the host side itself. Yeah, it would have given, since I didn't specify anything, it has given me some ephemeral port. So this is how you deploy on the Kubernetes side, and when you see on the Docker side, what exactly has happened is exactly as it would have happened, except that everything is now managed by Kubernetes. Now let's see what happens when we try to. Let's look at what pods are now running. What we saw inside Docker PS was there were 4 containers running, which Redis. I don't know why, because it was trying to keep them on the standby. But from the Kubernetes point of view, what it tells me that you asked me for 2 replicas, and I've started 2 of them, and they have been running perfectly fine. And let me do a Let me ask. I asked you to describe a particular pod. So let me describe this. Ask you to describe the pod. So it will give me all the images that there you go. So it is describing this pod in greater amount of detail. So if you ever want to see the container that has been started, it says this is where you will find it. And this is where I down the image ID where I downloaded it from. And this is a very important one. Pay close attention to this. This is one of the things that is so cool about Kubernetes. That is, it not only did all that stuff for you, but whatever happened during the course of the lifetime of the container, everything gets logged here, and this can easily be monitored. So this is the value addition that Kubernetes brings. That is, from one console, what you saw was I deployed it on one Kubernetes cluster, and it just so happens to have that Kubernetes cluster has one node, but it might as well have had 1000 nodes. The management from the Kubernetes console would have been exactly the same. And the way it happens on a single node is exactly as it would happen if you were using Docker commands and doing it yourself. But instead, you're using Kubernetes to go from imperative to declarative, and you're letting the system do all the work. And you're simply monitoring it, and Kubernetes takes care of the rest. So let's see, how do we stop the application in Kubernetes? Again, just like we use the Docker commands, we remove the deployment. There we did the Docker kill, and we kill the container. Here we don't do all those steps. We'll just say we created a deployment and we deleted it. Now let's see from the Kubernetes point of view what has happened on the deployments. There are no deployments. Absolutely nothing. So what happened on the Docker side? Oh, there you go. So the containers that were started by Kubernetes have been removed, but even the containers that were created, they have also been locally removed, but the images are not removed because the images will be reused and they may be vacated by Kubernetes whenever it finds it is not necessary. But this is in a nutshell the difference between how Kubernetes manages the cluster and Docker manages the cluster. And we observed what changes it makes to the C group file system. That means when a container is deployed, the control, it is placed under its own control group with all the limits that are specified when deploying the application and all the visibility limits. That means it is not allowed to see anything that it is not allowed to see, and it will not show anything, any devices that it is not supposed to see. So this way, the C groups and namespaces on the container host do all the work behind the scenes, and Docker is the layer that instructs the Linux kernel to do all this work. And at the next layer, the Kubernetes control program, which is kubectl, which is sitting outside of the Docker host from remotely. You will directly talk to the Kubernetes API server, which takes these requests, creates those resources, and then it communicates with kubelet, which will in turn communicate with the container runtime to make the whole magic happen. What I'm going to do is, I think this is pretty much all that I had in mind for you to try out on your own systems. But unfortunately, I could not paste it in the window. But I see something in the chat window. So let me just see if I can till chat window. So give me a minute. I could transfer these commands so that you could try it on your Ubuntu systems. A little bit of technical snafu here. I'm unable to go to the chat window, but really sorry about that. I don't know. I'm not sure why I am unable to access the chat window. But what I will do is I will share these files which have all these commands to you in the email via an email, and hopefully you will be able to see them. I will also try and post it in the summer school. So is there something that you wanted to see, and did you have any questions of any of this, or did you want to take a closer look at any of these? Please let me know, because I really wish I could share those commands so you could try it on your Ubuntu systems. Too bad you couldn't, but I would be happy to do those things here in my terminal window, so you get a clear picture of how all this came together to make the container magic happen. Okay, does anyone have any other questions that are related to today's class in terms of what C groups are, what the namespaces are, and what the container runtime means? What do we mean by orchestrator? And what do we mean by microservices? And what are all the various components in a Kubernetes slash Docker container ecosystem? So what we learned was that at the very basic in Linux, we have C groups, namespaces, and chroot, which allow programs to be deployed so that they have limited visibility and sort of they can be put in a jail. And a container runtime uses these to launch programs. In the value addition that the container runtime brings is that there is a specification called the open container specification, which specifies how a container image wraps around a program that you have built using your favorite language, to specify how this program must be deployed. And once that container image specification is uh, met and the image is created, it is put in a repo by the developers. And when the program has to be run, it is downloaded from the image repo and it is fed to the container runtime, which deconstructs the image, creates the necessary directories. And when instantiating it, it does all the necessary work of mapping the ports, providing the persistent data it needs, and opening up any ports necessary. And then it launches the container. And the Kubernetes is the one that helps manage these containers at scale, and it is in a declarative model. Instead of specifying the details of how exactly to open up and using long command lines, you can simply create the YAML files on the Kubernetes side remotely, not even logging in into the Docker hosts on the host, and simply specify what you want, and it will do all the magic behind the work to take that, create an object out of it, and it will ask a kubelet on each of the nodes to take and meet the requirements, as many replicas as you want, and as many rolling updates or any such thing you want. Everything will be taken care of Kubernetes. It orchestrates the container system. It even maintains the logs, and uh, that way it is able to scale to thousands of nodes. Whereas one instance with the Docker alone, you will be working on a single node. With Kubernetes, you can do it seamlessly across so many nodes. You will only have visibility to the containers or the pods that you have started, the applications you have started, and you don't really worry about the underlying infrastructure. And monolithic applications, which are single large binaries that have 1000 functionalities, all implemented as separate functions or daemons or programs, can be broken down into multiple programs that interact with each other, which are only invoked as and when necessary. That way, a monolithic system will not require as many resources as it would have. A microservices application would not really need so many resources as a monolithic program, because a monolithic program loads everything at once in the beginning, and the microservices architecture, you only load the parts that are necessary. And it is like, since you have a component wise picture, you can replace the parts without affecting the whole application. And that is a new way of doing things, and a lot of applications are being built that way. And that is becoming the foundation of the microservices. And as Adi had asked, it is more or less, you can think of serverless computing taken to the next level to bring a larger application to life as a collection of microservices. This is in short what you have learned. I hope it was useful, and I think we are nearing at the end of our lab session. And I want to thank you all for your patience, and I apologize for being unable to share the Docker and Kubernetes commands with you over the chat window. And I will send it out by email, and hopefully you will still have access to your Ubuntu systems, and you are able to get the Minikube going. Please continue with that and try these commands, and I'm sure that you will find a lot of things interesting. And in the coming days, you will see that most of by the time you graduate and come out, you will see that most people are just talking about containers and microservices and how to deploy applications. And hopefully this knowledge will help you with fitting into that ecosystem. So I'm going to now open up for any questions, any comments, or anything. After this, I think we will close this class, and we will disperse. Anyone, any thoughts, any closing comments, any requests on from me? Anyone?
Hi.
Hi.
Thank you for the tutorial. It was really great. I have a different question. Is that okay if I ask?
Absolutely.
Sure. So I would like to, I mean, yeah, this is great. And obviously Docker and Kubernetes is the future, but my understanding is that Docker and Kubernetes are basically innovations in software engineering and program execution, right?
Mm-hmm.
The underlying system stack is not changed. Right, the storage is the same, the memory is the same, the CPU is the same.
Yes.
We basically made some changes at the middleware level and above the middleware in the application level.
That is correct.
So what changes in system software can be made which help improve these containers and which help improve the performance, latency, energy efficiency of these container-based applications? I mean, where in system stack would you like to see changes made?
So I think that is a great question. So a lot of innovations are happening in the system space. For example, you heard about converged Ethernet. That means Ethernet has become the standard fabric over which many of the higher level protocols or technologies, for example, NVMe OF and um, uh, and other protocols, iSCSI or any of those protocols, they all run over Ethernet today. There are not many other fabrics that are being used, and there are plenty of other technologies like RDMA and other things being built. And containers are essentially every innovation that happens today. For example, you are trying to build something in a hardware acceleration or anything. How do you expose these services to containers? For example, if you give a dedicated hardware, how do you provide the address isolation? Yesterday you learned about how the IOMMU and other things operate. But even today, if you see IOMMU and all these things, they are targeted towards a particular host. And any of the when you learned about the virtual memory, about how it is accessed, you saw that in a physical host, the address translations that are kept in TLB are still at the VM level. That is, it stores all the addresses that are accessed by the virtual machine. It does not make any differentiation with respect to this container. So for example, a container came in, it accessed a whole bunch of memory, then it went away. The addresses that it has accessed will still remain in the system TLB cache. The system still thinks that this virtual machine is again going to access those virtual memory, whereas the container that is responsible for accessing that memory is long gone. Same thing with IOMMU. So a lot of things today that are happening in the system advancement space are not fully connected with container. For example, GPUs and other things, they are not really, how do you allow a GPU to be shared amongst containers without compromising on security? How do you provide secure encryption channels to only containers and prevent any other program from compromising it? And the other aspect is you have even to this date, you will keep seeing system vulnerabilities that are being reported on Linux, whether it is on Linux or it can come from the processor that you saw in Spectre and Meltdown issues that surfaced a few years ago. So many of these things will allow one container, a rogue container, to go rogue and access the kernel. And once it gets into the kernel, it's suddenly invaded every other program that's inside that is hosted by that kernel. Whereas this would not happen if you had two applications running in two virtual machines. If one virtual machine is compromised, the application running on that virtual machine is compromised and nothing more. Now, in the container world, when one virtual machine is compromised, virtually all containers are compromised. So where do you draw the line of securing the containers? Do you need to do a different type of virtualization inside so that you have silicon root of trust? That means in virtual machines, one virtual machine is isolated from the other by means of silicon root of trust. That means the processor is the one that ensures why it doesn't mix up it doesn't allow one VM to interfere with another VM. So the same kind of silicon level of guarantee is not available with containers. So maybe this is an area where much innovation can possibly occur in system space. Of course, these innovations are occurring in higher layers also, where they say we do not require any change in the silicon in the processor or anything to support containers. But I believe there is still scope for any of the system advancements to come to the container world. Does that make sense, or did I confuse you a bit more?
No, that's a great answer. Yeah, this is very interesting. Definitely, I agree with your points. I especially like this point of providing support for accelerated hardware,
Yep.
and that is one important direction I see.
Yep, absolutely. Any other questions before we adjourn? Okay, I want to thank everyone for coming to this class. I hope it has been useful, and I hope when you go out into the container world, the basics that you have learned here will be useful to you. This is by no means exhaustive. As you can see, container is something that you cannot simply become a master of in 2 hours or 3 hours. It takes a lot more effort than that. But I hope I've given you a good introduction, and I wish you students all the best in your pursuit of knowledge of the container technologies. Have a great time, and we'll meet again tomorrow in the final class for the school. Thank you, everyone.
Thank you. Thank you. I have one last question.
Sure. Please.
Thank you. Thank you for your time. I don't want to hold anyone back. So this is a very, very hypothetical question, but yeah. So containers have been around for years now, right?
Mm-hmm.
What do you see as I mean, back first we had hardware, then we had operating systems, then we had virtual machines. Now we have containers. What's next?
It's I think in one of the earlier sessions also I said the future is um, it's very dangerous to predict the future, especially if you are not inventing it. And I am although I see a lot of innovations happening about where it goes. The innovations that I see in the container technology is where most of the innovations are occurring in terms of uh, how the computing facilities are brought to the end user. So many of these functionalities are to be injected. For example, you might have seen the recent COVID pandemic. Everyone was trying to say there are no hospital beds, and in the future, if a bigger pandemic breaks out, would it be possible for everyone to get a bed if they like, or what is the alternative? So there are some disruptions occurring there, or likely to occur there, which says, okay, I have a house, and how soon can I, if I have one sick person, instead of trying to roam around the city trying to find a room or trying to find a bed, hospital bed, I can convert one of the beds in my house into a hospital bed, and I'll put some sophisticated equipment in there, and I will have 5G connectivity, so I'm all set. And probably there will be the all the monitoring, whether it is system vitals monitoring or the blood monitoring or any other monitoring things will automatically be downloaded into that equipment, and that equipment is easily hooked up to the patient, and it is available to any doctor anywhere in the world to monitor it as if they were in his clinic or in his hospital, and offer the suggestions, and any medicines that are dispensed uh, would be also would only need to be fed to the machine, and the machine takes care of administering them. So there are many of these things that are happening, and the technologies that are available uh, in terms of program execution are there. And every time we hand off something as important in our daily existence, whether it is um, uh, delivery of medicines by drones, or whether it is handing off the controls of airplanes and rockets to computer programs. The challenge always remains on how do we ensure that if something goes wrong, it doesn't end up in something being catastrophic, and multiple levels of failure and other things will likely take over. So in terms of program execution, newer form factors and newer ways of delivering functionality to the places where they are most necessary will likely take place. And many of these the drivers basically come from faster networking and more sophisticated equipment. Today I was mentioning, not today, in one of the classes I was mentioning the availability of Raspberry Pi, I mean the last Saturday. So you have very powerful systems available to our disposal in very small form factors, and the programs also have to keep up with how they are used and how they are deployed and how they are managed and how they are secured. So I think a lot of innovation will occur in that area. That's just my guess, since you asked.
Well, that's great. That's really good to hear. I hope these things do come true. Thank you.
Yep. I mean, disruptions will occur where we least expect it, and I hope they continue and make our lives better, and uh, all of you will likely play a big, small or medium, whichever part in it. And I wish you all the best.
Thank you very much.
Thank you, everyone. I wish you all the best, and I'll talk to you soon again. Thank you.